This robotic actuator, this jumping robot that also draws, and this quadrupedal robot leg all share one thing in common. They're each driven by rope. Gears are everywhere, in our tools, in our machines, and in our robots. But if I'm being honest, gears are so 3rd century BC, it's time for something different. This project took several months to complete, with tons of prototyping and even more testing. So today I'll be sharing my entire journey in making what I consider to be the most underrated reducer in robotics. So why rope? Well, gears have this little thing called backlash. You can think of backlash as the gap in between the teeth of a pair of gears. And gears need backlash in order to mesh properly, but backlash also limits precision. And when you're building a robot, precision is extremely important. Gearboxes can also be pretty noisy, especially if you're like me and you prefer to 3D print them instead of spending a bunch of money on some high precision metal ones. The rope-driven reducer that I built in this video is called a capstan drive. And the benefits of a capstan drive include being really quiet, having zero backlash, high torque transparency, low inertia, and best of all, being extremely cheap. In fact, all the manufactured components in this video were 3D printed. And besides general strength, there really wouldn't have been any other performance differences if I were to have made them from metal. I first heard about a capstan drive when I saw a robot named Stanley by a company called Ahead.io, which I'll link below. I thought this was a pretty interesting idea, so I decided to prototype my own capstan drive using shoelaces from an old pair of Nikes.
Bruh. What?
A capstan drive has a smaller drum and a bigger drum. Just like with gears, the reduction ratio is calculated by dividing the big drum diameter by the small drum diameter. The kicker here is that instead of using teeth to transmit torque, a capstan drive uses rope. The rope wraps around the smaller drum and is put into tension on both sides. This way, as the drum spins, one side of the rope gets shorter while the other side gets longer. Now, if you're like me, then you're probably asking yourself why exactly the rope doesn't slip if it's just wrapped around the smaller drum, especially if we were to apply a heavier load. Now, the short answer to this question is because of friction, but the longer answer to this question is still because of friction, but more specifically, something called the capstan equation. Let's say we have rope wrapped around a fixed drum, and let's also say that the rope is put into tension by applying a force T-load and T-hold onto either end. We can think of T-load as being a weight, and we can think of T-hold as being the force that a person applies. Now, if the system was perfectly frictionless, then Newton's third law would tell us that the person needs to apply an equal and opposite force to our load in order to keep things in static equilibrium. Luckily for our person, this isn't a perfect system, and we do have friction, which means that our person only needs to apply a fraction of the load force to keep things in equilibrium. To be exact, T-hold only needs to be equal to T-load divided by e to the power of mu theta, where mu is the coefficient of static friction between the rope and drum, and theta is the angle of wrap in radians. And that's the capstan equation. What it tells us is that if we hold T-load and mu constant, T-hold decreases exponentially with the number of turns of rope. And to illustrate just how useful this concept is, let's say we have a system with a coefficient of friction of 0.6 and only 4 turns on the drum. An average person could produce enough force to hold 2 Titanics. And what's even more surprising is that there's still not enough turns in the world that could hold yo mama. The capstan equation shows us why the rope doesn't slip on the small drum. Given the right amount of turns, usually around 5, there's enough friction to prevent slipping with really high loads. In fact, the term capstan refers to a device used on ships to multiply human pulling force when hauling in rope. And the same principle applies to a capstan winch. You can use friction to help you do work. The first device that I plan on making is a capstan actuator. And to do that, I'm using a 90 kV brushless motor and an ODrive S1 controller. This controller uses field-oriented control, which basically turns the brushless motor into a high-precision servo. To make the actuator, I used 1.5mm stainless steel wire instead of shoelaces, threaded 4 screws into the smaller drum to increase its strength, wrapped the wire under the drum instead of over the drum to minimize vertical forces, used a lead screw to tension the wire, and made the gear reduction 8:1 to make it a quasi-direct drive. And just like that, we have our first prototype. The first thing that I noticed was that this thing is smooth like butter. You gotta just watch it run. Looking at a capstan drive, you'll notice that one of its disadvantages is limited rotation. For this reason, I think a capstan drive is best for highly dynamic robots like quadrupeds or bipeds, since those robots don't necessarily need actuators with full rotation. A capstan drive can also be really good for haptic devices. Limited rotation isn't all bad because it means we have physical limits. With physical limits, we can program homing sequences. I programmed two different homing sequences. The first one is called two-stop homing, which moves the actuator to both physical limits, calculates the gear reduction, and then finds the middle position. The second sequence, called one-stop homing, just goes to one physical limit and uses an already determined gear reduction to find the middle position. In both cases, it's able to detect the physical limits by measuring the current draw of the motor. Now, you may correctly point out that I said the gear reduction is 8-to-1, and so there really shouldn't be any point of using two-stop homing, since the gear reduction is always known. But for reasons that I still can't understand, when I calculate the reduction in software, it isn't exactly 8-to-1. It's about 8.5-to-1. I think in part this has to do with the helical pattern of the smaller drum, but I also tried adding a helical pattern to the bigger drum and still couldn't get an exact 8-to-1 reduction. I ended up just keeping it at 8.5-to-1 and calling it a day. So the purpose of two-stop homing is to calculate the exact gear reduction in software, since we can't use the drum diameters to calculate the gear reduction. I prototyped several different drum designs with different shapes, sizes, and mounting points. Eventually, I settled on one that worked best and moved on to endurance testing. The goal here is to just run the actuator for a long time and see what happens. But unfortunately, just 4 short hours later, the steel wire broke. And to make sure this wasn't a fluke, I ran the test 2 more times, and in both times, it never crossed the 5-hour threshold. Now you may assume that using a thicker cable would solve this problem, but you would be wrong. In fact, a thicker cable would actually be worse. And I know this because of something called a D-to-D ratio. A D-to-D ratio is the ratio of drum diameter to rope diameter. And as it turns out, the D-to-D ratio of stainless steel wire needs to be really high. In other words, the diameter of the small drum needs to be significantly bigger than the diameter of the stainless steel wire in order for it to not fail from fatigue. My current D-to-D ratio is about 10.7, but according to my findings online, I've seen the minimum D-to-D ratio for stainless steel to be anywhere from 15 to 30, which definitely explains why it failed. So stainless steel wire is pretty much a no-go, so I guess it's time to try synthetic rope where the minimum D-to-D ratio is much lower. I got some 1.5mm paracord and continued endurance testing. Fortunately, there wasn't any failure this time, so I moved on to load testing, which was when I noticed another issue. With any kind of reducer, you have to consider its life cycle. With gears, you have to worry about wear due to friction over time. And with a capstan drive, you have to worry about creep over time. Creep is the permanent stretch of rope, and this channel is a creep safe zone. No matter what rope it is, if you put it in tension, it will stretch. It's just a matter of how long until it stretches by a significant amount. Unfortunately, a lot of synthetic ropes have higher creep rates than what we would want from a precision actuator. And this is probably what I would consider to be the one major flaw of a capstan drive. It can lose precision by just sitting down over a period of time. So how exactly do we solve this? Well, you'll never guess, but the answer is to just find rope that won't stretch. After reading some academic papers, I found 2 candidates, Vectran and Dyneema DM20. DM20 is a newer rope, and it seems to be the more promising option, since it claims to be the most inextensible rope on the market. It's also almost exclusively sold in Europe, but eventually, I got my hands on some. I built an actuator with both ropes and let them run for a really long time to test just how inextensible they are. While this was running, I also ran a static creep test with the stainless steel wire, the paracord, the Vectran, and the DM20. I put them into tension and retensioned them over a period of several days. As expected, the paracord was really the only rope that extended significantly over the period of time. Right as I finished that test, the 1 week mark had just passed for the dynamic creep test. The Vectran not only seemed to have extended, but it seemed to have weakened since I could stretch it further by hand. The DM20 seemed to be completely intact with no notable signs of extension. I continued testing with just the DM20 actuator for another week, and it still seemed to be perfectly intact. So DM20 by far and away seems to be the perfect rope to use when it comes to a capstan drive. I was curious about the accuracy of the actuator, so I built a new one with these 10-degree tick marks. This lets me know that the code completes the humming sequence properly and calculates the gear reduction properly. If you're curious about speed, this is how fast it can go. Another important test for any robotic actuator is load testing. I started off by having it sling around 2.5 pounds. I then moved on to 5 pounds, and then I performed a torque test and got around 13 Newton meters. Now a capstan actuator might be fast and precise. The second device that I'm going to be building is a 5R parallel robot, which is just a really fancy way of saying 5-bar linkage. Unlike most conventional 5-bar linkages, this one is coaxial, meaning that the driving shafts share a rotation axis. This is going to save a lot of space and also simplify the inverse kinematic equations. Inverse kinematic equations essentially allow us to find the motor positions needed to move an effector to a point in space. Now, I'm not going to get into the math involved with the derivations. That's a whole nother video on its own. What I will say is that the math is pretty much just basic trig. In fact, I'm convinced that you can break down any complex robot's geometry into a series of solvable triangles. After deriving the equations, I printed the parts and assembled everything together. This is what the startup calibration sequence looks like. It homes each actuator one at a time to ensure that they can each reach their end stops. When it comes to programming a robot, one of the most important things is kinematics. We've talked about inverse kinematics, but kinematics in general just describes the motion of an object without considering the forces that cause that motion. When programming movements, a big question is how do we move the effector from point A to point B? The inverse kinematic equations already allow us to move our effector from point A to point B, but the issue is there's an infinite number of ways that we can get there. So if we just shoot it from A to B, we have no idea which one of these paths it'll take. What we need to do instead is interpolate. When we interpolate the position, we're essentially moving to a bunch of subpoints in between our main points to get the exact trajectory that we want. Of course, there are different ways to interpolate. We can interpolate linearly, exponentially, sinusoidally, and so on to get different trajectories. To demonstrate this, here the effector is moving from A to B without any interpolation. And here, the effector is moving from A to B with linear interpolation. To further demonstrate this point, we can trace out a square without interpolation. We can also trace out a square with interpolation. We can even trace out a triangle with interpolation and a circle with interpolation. Now, you might be a bit skeptical about the accuracy of those movements, but trust me, they're accurate. And if I still haven't convinced you, then let's trace out those shapes again, but this time with a pencil attached to the effector, so we can see exactly what it's tracing out on paper. So, once again, here the effector is moving from A to B without any interpolation. Here the effector is moving from A to B with linear interpolation. Here is the effector drawing a square without interpolation. Here is a square with interpolation. Here is a triangle, a circle, a diamond, a sine wave, and a combination of a square, circle, and diamond. And as an added bonus, here's the robot almost drawing shapes successfully. Now, I'll be honest, drawing is pretty boring. Let's make our drawing robot do something a drawing robot shouldn't be able to do. Let's make it jump. Eventually, it jumped a little too much and broke. But I mean, if you aren't breaking your robots, then are you even pushing them enough? The third and final robotic device is a quadrupedal robot leg. Quadrupedal robots are easily my favorite kind of robot, and I think building one like Stanley with a capstan drive would be awesome. So I'm building a test leg to see just how awesome it could be. Just like with the 5-bar linkage, the first step is to figure out the inverse kinematics. Normally, in a 12 degree of freedom quadruped, a single leg would have 3 degrees of freedom. But since this is early testing, I'm going to dumb it down to just 2 degrees of freedom. I still went ahead and solved the full IK equations for the 3 degree of freedom case to use in the future. It's just that some of these terms are going to go to 0 for the 2 degree of freedom case. You'll notice that I made the design of the 5-bar linkage and the quad leg pretty similar, since A, they both use the same coaxial design, and B, it saves me parts that I have to print. A lot of the code was also the same, as you can see with the startup calibration sequence. And just like with the 5-bar linkage, we can trace out pretty much any shape. Now, admittedly, 1/4 of a robot dog can't do much. But one thing it can do is jump. So let's try that out. And just like before, the fun came to an end when a 3D printed part broke. I'm not too worried about this, since we can always strengthen 3D printed parts by changing the material and/or settings. The most important thing is that the rope didn't fail. Also, more than anything, this video is about testing, so I fully expected to test things to failure. Throughout this entire video, I have redesigned this test stand so many times. The latest design, which I kind of showed off in the beginning, has a more even distribution of tension on the lead screw, a covering for the controller, and a more simplified drum design. It also has 120 degrees of rotation and weighs about 852 grams. If you are interested in making this test stand yourself, you can download the model as well as the bill of materials in the link below on my GitHub. So, a capstan drive. Probably my favorite reducer at the moment. Might not be as compact as a planetary or cycloidal gearbox, but I think for what it lacks in compactness, it makes up for in performance. I'll definitely be using this in future projects, so be sure to stay tuned. Thanks for watching, and feel free to subscribe if you feel so inclined to.